Hello, George Romanic here. Welcome to Fundamentals of Weather and Climate playlist. In your freezer, water will freeze, hence the name freezer. Temperature in a freezer is below 0 degrees Celsius, and if you put water there, after short period of time, it will freeze. However, I am here to tell you that water can stay liquid below 0 degrees Celsius. How can that be the case when from everyday life experience we know that water freezes below 0? We also studied that in elementary and high schools. Well, the phenomenon when water is liquid below 0 degrees Celsius is known as supercooled water. And just to blow your mind, water can stay liquid all the way to temperatures of about negative 40 degrees Celsius. That is extremely cold. In fact, in clouds, water is almost always liquid at temperatures of about, let's say, negative 10 degrees. How is that possible? Why is water in freezer freezing, but not freezing in clouds at, say, negative 10 degrees Celsius? Does the water know it is in freezer and, oh, I need to freeze, whereas in a cloud or somewhere else I need to stay liquid? In a sense, it does know. And that's what I will explain in today's video on the phenomenon of supercooled water. Well, to start this video, it is very important to say that yes, temperature plays a very important role in freezing of water, but temperature is not the only contributor. The other contributor is the first ice nuclei, ice embryons that develop in a volume of water. In other words, in simpler words, when you have a volume of water, like a glass of water or a droplet, that volume does not freeze instantaneously everywhere when temperature drops below 0. Instead, what happens is that we have small nuclei, small embryons of ice forming somewhere in that volume of water, and then from those nuclei, the ice continues expanding and eventually the entire volume of water will freeze. And that's very important because you will see now that we have two options when it comes to those embryons, those nuclei. Option number one is we have 100% pure water, H2O. And option number two is water is not 100% pure, but there are some impurities or foreign objects in water. In these two cases, the process of freezing is different. So let us first discuss case number one, when water is 100% pure, there is nothing else in water. In that case, consider a volume of water of this size. Okay, so this is volume of water, and let's say this is volume V1. Temperature is below 0 degrees Celsius. So what will happen in this volume of water, randomly, somewhere in the volume, let's say we have 3 ice embryons that develop. I will indicate them with these snowflake-like symbols. So we have these 3 embryos that randomly form. Now, what does that mean that we have these 3 ice nuclei or ice embryons? Well, if you go back to my video on why water is so special, then you know that in ice we have crystalline structure of water molecules that is rigid and it forms ice. Whereas water molecules in the surrounding liquid water do not form that hexagonal crystalline lattice, where they are rolling on top of each other. Well, this is now a very important sentence. Thermal jiggling in this liquid water is higher than thermal jiggling in these embryons of ice that are forming initial crystalline structure. That means that thermal jiggling in this liquid water will bombard these embryons and destroy them. So randomly, because temperature is below zero, small particles of ice might form somewhere in liquid water, but thermal jiggling of water destroys them. So they are constantly popping up, but they are also constantly being destroyed. So what needs to happen for this volume of water to freeze is that one of these embryons needs to survive long enough to acquire more and more liquid water molecules that are freezing, and then the freezing will expand throughout this volume of water. The issue is they cannot survive long enough because of thermal jiggling and surface tension inside of the water that we will discuss later. So, in other words, if there is probability that we need to assign for any of these embryons to sustain freezing, namely to acquire more liquid water that will freeze, or being destroyed by thermal jiggling, probability for being destroyed is always higher. But now, look at this beauty. Now I applied the same reasoning I just outlined, but for much bigger volume of water. Here I have much bigger volume of water, let's call it V2. And the temperature is negative. In both cases we keep the same temperature, let's say negative 10 degrees Celsius. And it is very clear that volume V2 is larger than volume V1. If I randomly had per unit time 3 embryons in volume V1, well, then it is very clear that I will have more embryons in volume V2 because V2 is larger. So if I had 3 here, let's just say here I have 10 then. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How does this matter? Greatly. Because, very important sentence, I said probability that any of these 3 will be disrupted by thermal jiggling and surface tension is higher than them surviving long enough to spread freezing. The same concept applies here, but here I have many of them. Here I had 3 of them. Probability is small that they will survive. So, probability is applied to these 3. Probability is also small that they will survive, but here I have 10. So probability that one of these 10 will survive is much higher than probability applied to these 3. And therefore, the larger the volume of water, the higher the chances we will have embryons that will survive long enough against thermal jiggling and surface tension to sustain freezing. This can be quantified, but as you know, watching this playlist, this is playlist on the fundamentals of weather and climate. So I don't go here too much into equations. That's reserved for my advanced playlists on Thursdays, and although I partially stopped publishing these because I'm so busy on these fundamentals, but anyways, what I want to say is this can be quantified. And I can just write equation without deriving it. So if we, let me erase this. Because this equation is absolutely beautiful. If I say that J is ice nucleation rate. What does this mean? It's a fancy term to say this is number of those ice embryons per unit volume per unit time. In other words, how many ice nuclei or ice embryons we form per unit volume and per unit time. Then probability P that any one of these embryons will live long enough to sustain freezing is 1 minus e exponential function to negative J times volume V times time T. Very important equation, very beautiful equation. Everything I just bragged about for 5-10 minutes is in this equation. Because, you know, if you know a little bit of mathematics, I can write this as 1 minus 1 divided E to J times volume times time T. Look at this now. Look at this beauty. Look at this beauty. If I increase volume, if volume increases, that means from this equation, this exponential function will increase. But 1 divided by this exponential function will therefore decrease. So as volume is increasing, let's say tends to infinity, this is tending to 0. So this further means that this is 1 minus some very small number. And that means it's approximately 1. So probability that we will have freezing as I am increasing volume is approaching 1. In other words, for huge volumes, we are almost certain to have freezing. So you see, volume of water plays very, very, very important role. The smaller the volume, smaller number of these embryons that will form and potentially sustain freezing. How does temperature play the role? Well, temperature plays the role in this J, ice nucleation rate. If we decrease temperature, you remember this small volume of water, we initially assume there are only 3 embryons. Well, if I decrease temperature, then in the same unit of time, I might have 6 embryons that spontaneously form. And that will again increase probability of freezing. That is why below negative 40 degrees Celsius, there are so many ice embryons formed in any volume pretty much of water that freezing is almost certain, even if water is 100% pure. And again, what is the influence of time? The longer we wait as the time is running, the longer we wait, the probability of freezing increases. That's also logical. I believe this equation and the phenomenon how water can stay liquid below 0 degrees explained to these embryons and ice nuclei is absolutely beautiful. Now, if we apply that to your water in freezer, if we apply this to your water in freezer, first of all, application cannot be 100% accurate because water in your freezer is not 100% pure. And here we are discussing the 100% pure water case. But if we do assume that water in your freezer is pure water, then if we have a glass of water, liquid water, that you put in freezer, that liquid water has volume V. Now this water is touching containers. If we neglect this is extremely important, but even if we neglect that the water is touching containers, this volume of water is enormous. This is what we would call macroscopic volume of water. There are trillions upon trillions of water molecules. And for these enormous volumes, probability of freezing is very high, so your water is very, very, very likely to freeze in the freezer. But the effect of the container cannot be neglected because these impurities or foreign objects immersed in water play extremely important role. And that's the second part of this video, because what we discussed now is 100% pure water. But water is rarely 100% pure. So the question is how foreign objects and impurities in water promote freezing. That's what we will discuss after I erase this whiteboard. to start this part of the video, imagine that this whole whiteboard is liquid water. And in that liquid water, I have this embryon of ice. So this is liquid. This is ice. And temperature is below 0 degrees Celsius. Now, you know that ice expands when water freezes. I described that in great details on the video on why water is so special. So ice tends to expand, but liquid water, through pressure and particularly surface tension, wants to undo this expansion. How surface tension works is a subject of my previous video, so please go to my previous video and it is described in great details. But surface tension acts inward, trying to undo this expansion. So you see, if this embryon of ice is immersed in this liquid, pure liquid water, then this surface tension term, again, it can be quantified through equations, tends to be stronger than the expansion of ice, and the ice will melt. This small embryon of ice will melt. However, look at this beauty. What happens if we have impurity? Imagine that now here this is some impurity in water, maybe a wall of a glass, or maybe some mineral in water, or something like that. Now imagine that, so this is some impurity, and imagine ice embryo forms here. This blue ice embryo forms here. What do you see as the difference? Well, you see as the difference that the surface tension and jiggling in water act from liquid water. So this is ice. This is liquid. Again, temperature below 0. You see that the surface tension and thermal jiggling are acting from this direction, but this side of ice nucleus is protected. It's protected from this effect of surface tension by the impurity, by the foreign object. So ice has much greater chance to expand, to acquire next layer of liquid water molecules that will freeze, next layer that will freeze. The freezing might continue in this direction, and the freezing will spread throughout the liquid water volume. So the role of these foreign objects is to shield, to protect those embryons of ice that form next to them from the surface tension, pressure and thermal jiggling of liquid water. And that is why if we have foreign objects, impurities in liquid water that is below 0 degrees Celsius, it is very likely that the freezing will initiate next to these foreign objects. There is another detail I could add here, and I will now, that if these foreign objects, if these impurities have crystalline structure that is similar to hexagonal crystalline structure of ice, that additionally helps. Because then ice and this impurity are similar in terms of microscopic structure, both are crystalline, so the ice can naturally, so to speak, continue forming on this foreign object. Typical substances that are very good to sustain ice formation is silver iodide, kaolinite, which is natural ingredient, dust found in the atmosphere, and so on. I will talk about that in one of the next videos, but for now you can remember that. So this video explains two things. Number one, how ice can form in pure water, no impurities, and how ice can form in the presence of impurities, which is typical case because water you drink from in your kitchen is not 100% pure water. It has all kinds of minerals, impurities, dust, and so on. So when you put that water in freezer, there is plenty of surfaces on which ice can form. And moreover, as I just discussed, when you put it in freezer, there is also a container. And that container that is touching water is basically this. Okay? So that's why water will almost always freeze in your freezer when temperature is below zero. But in small microscopic particles of liquid water in the atmosphere, that need not be the case. And that phenomenon is known as supercooled water. Why does supercooled water matter in the atmospheric sciences? Because, as I said at the beginning of the video, most water in clouds at temperatures negative 10, 15, 7, 12, whatever degrees Celsius is liquid. But if there is small embryo of ice in that liquid water, that does play enormous role in terms of how cloud grows, how precipitation develops, and so on. And that's what we will discuss later in this playlist. But to discuss that later, I first had to introduce the concept of supercooled water. Thank you for watching. Please make sure to like and subscribe, comment and share this video. And until next lecture, goodbye.